Hello everybody and welcome back to another Microsoft Excel tutorial. In this tutorial I'm going to be showing you how you can forecast using Excel graphs. And Excel graphs are very powerful for forecasting. For those of you that know me, you know that I use them a lot at work because I forecast a lot of things. And a lot of the times if you want a very quick and easy but still fairly accurate forecast, then Excel graphs are really handy. So here I have some data, and the example I'm going to be using is forecasting global warming. So please don't take me too literally if I get the stuff wrong. You know, I'm not going to start saying it's the end of the world or anything. It's just quite a nice data set to use and quite a real world example that a lot of people can relate to. So over here in our yearly averages, I have the year. I have a number which is I'm going to be using for forecasting in a minute, which I'll show you, and then I have the average temperature in degrees Celsius. I also have the averages over the 100 years data that I've got. I've got 104 years data that I've taken off the Met Office website. I've got the monthly averages, and then over in here you can see I've then got the yearly average as a graph and the monthly averages as a graph. All the way from 1910 up to, well, 2015 this goes up to, but it's saying 2016 here just because there's multiples of 2. Anyway, so here is our graph, and we're going to use a trend line, which I used a couple of episodes ago when we went through scatter graphs. I'm going to use it again here. I'm going to use it on a line graph, and you can use it on the majority of graphs. I'm going to right click on the series, make sure you're clicking on the series, add trend line, and then I'm going to start off showing you through a linear one. So this then gives us a linear trend line. If I scroll across, you're able to see it now. And you can see it goes up gradually over the 100 years or so. So from 1910 through to 100 years later, 2010, you can see it's gone up 1 full degree Celsius, which may not seem like much, but each degree Celsius is just under around about 2.5 meters of sea level. As an FYI, these are UK temperatures. If you're in one of the more exotic countries around the world, then you'll get better temperatures than this. Not that I'm complaining, that would be a very British thing to do, but not what I'm doing. I don't think. Maybe I am. Who knows? Anyway, so over the last 100 years, the sea level should have risen by around about 2.5 meters because the temperature's gone up by around about 1 degree Celsius. So it would be fair for us to expect then that over the next 100 years we'd see the same thing. So we've seen a change of 1 degree over the last 100 years, so it would be reasonable to expect it to carry on going. And this is what we call a linear trend line, whereby the change over a certain period of time is going to be the same no matter which period of time we're looking at. Now, there are other ones that we can use, and I'll come on to those at the end of it, but to start off with, we're going to stick on these linear ones. Now, you might be wondering when we're going to get to the forecasting. So if we come down here and we look at our forecast options, you can see we can forecast forward and backward a certain number of periods. In this instance, our periods is years because that's each one of our records, and here is 1 year. So if we put in another 100 periods, then we should get it going out on another 100 years, and you can see that it's gone out here. Our x-axis doesn't quite go all the way to the end of our data, so let's just edit that. Come in here. And we don't want it going down to 108, we actually want it going down to 206. So if we just edit that in our x-axis to give us the labels that we want, press OK. And now you can see that our labels go all the way out to 2114. And can we imagine that I'll be alive to say I told you so, but in another 100 years time we're saying that the average temperature should reach around about 10 degrees, which would mean we'll be another 2.5 meters underneath the water. which doesn't seem like a lot, but when you think about it in terms of all around the coastline, everything's going to go 2.5 meters under, it suddenly has quite a big impact. So, moving on, we would quite often want to take this line and put it back into our column data. So here I've got a column that says predicted average. And when we go down here, we're going to want to see what that predicted average is against our actual data as a number. And it's going to be even more useful when we come on to a bit later when I want to be predicting the monthly temperatures. So when we go into here, what I'm going to do is I'm going to click on our trend line, and I'm going to click on this option down here, which is display equation on chart. Now, I've already been playing around with this, so it's got a couple of extra options in it. I've clicked on it and I've changed the font value up. And the other thing I've done is in here, I've changed it to a number format and I've increased the number of decimal places by selecting number and then putting 10 in this box here. And what this does is this is going to give me the formula, and because I've got the extra decimal places, it's going to make it so I've got a really accurate figure here, which if you have large numbers as your X's and your Y's, then this is really important because otherwise it throws your numbers out quite considerably. So what this is saying, and for those of you that know how straight line graphs work, you'll know that this number here is our gradient of our line, and this number here is our intercept at the x equals 0 value. So you can see here, that's around about our intercepts of our y-axis. Bear in mind that x is based on periods, and each period is 1 on here, so our 1910 figure is the number 1. At x equals 0, it's basically 1910. Yeah, so this gives our formula. So this is the change every single period. It goes up 0.086, and this is where our graph starts. So we're going to copy this, and we're going to go into our year averages. I'm going to paste this out over here. I'm just going to keep it the same size so it doesn't mess up my row things. And then I'm just going to take the gradient. I'm going to stick it underneath just so I can reference it in a formula. I'm going to take our intercept and stick it underneath so I can put it in a formula as well. And I'm just going to write that down what they are in case I forget. Intercept. Think about how it was spelled then. Okay, so now we've got a gradient and our intercept. So in here, we're going to put equals. So the cell is going to be the value y, and then we're going to do our gradient. F4 times x, so times, and then this is why I've got this number column in here, because technically 1910 is our first one, so our value is x is 1, and then I'm going to put plus the intercepts, and I'm pressing F4 to give myself the dollar signs. If you've watched my absolute referencing tutorial, which I'll put a link in the description below, then you'll know that stops it from when I next come and drop the formula down. It means they're still going to be referencing these ones over here. They're not going to drop down like the one without the dollar signs is onto the next row. So this then gives us our predicted averages. And if I press this button a few times, it's going to make it a little bit easier to read. And as we go down, so if we go to the bottom of our actual data, you can see now 2016, which is the year I'm doing this tutorial in, all the way out, we've now got a predicted yearly average for our temperature. And this should match with our line over here. Now, that's very useful. We've now got ourselves a forecast. We've got all the numbers every single year. You can see when it gets to the end, it's going to be 9.77, whereas at the start it was 8.12. Now, some of you might be thinking, well, that's not necessarily representative of all the time. We don't always see a linear trend going up like this. It's not always consistent over time. And this is what our other options here are for. So we've got an exponential, and those of you who've studied mathematics will know that an exponential will increase in over time in the gradient of it, how fast it's going up. So if I put this out to say 10,000 periods, which is a bit extreme, and probably too extreme, but you can see that it's going to go up a lot steeper towards the end and then be slightly curved in the middle. And so over time, the gradient is going to change, which in this instance, if I come back to our 100, so if I click on our trend line and change this back to 100 periods, you're going to see it isn't going to make an awful lot of difference because it's going up slowly anyway, that any change over time isn't going to have a material impact in the near future. And even if we say like this over the next 1,000 years, then it doesn't really look overly exponential. 1,000 years, it's going to be an average of 22.5 degrees. But yeah, we're not looking out to 1,000 years, we're looking over 100 years because that's more relevant to us as a generation, or several generations, I guess. Anyway, so if we want to use the exponential, we can do the same thing again. We can copy this out if we want to. We can put it into our yearly averages as a formula. So we take this. This time it's not so much gradient and intercepts, and I don't really know if they've even got official names from what I can remember of studying mathematics, but the concept for putting the formula together is still the same. We've still got our x value. We're using the value e, which is a mathematical number. It's around about, I can't remember what the value of e is. If we do equals exp to the power of 1, 2.718282, blah, 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 blah. Some people know it off by heart. I don't, because I haven't studied it for so long, but I do use it a lot. But you know, once it's the value of e, you kind of forget what it is. Anyway, we're going to do equals again because our cell is equal to the y value, and then we're going to take our transformation number here. We're going to times it by exp, which is what gives us the value of e, and then in our brackets we put the 0.09999 times by our value of x. And close that off. Remember that our 0.0009 needs to have our dollar sign so it doesn't change as we drop it down. And then you can see now that we've got our new one, and they're very, very similar to each other, but this is only in this example. In other examples, it will give you much more difference between your two figures. And once we go down to 2114 at the end, if you're wondering how I'm quickly dropping to the end, it's control and then down and up, just takes you to the bottom and the end of the data. You can see there's only 0.4 of a difference, which is still, you know, a good meter or so. And that's how you can quite easily, with the same data, come up with different forecasts, people using different methodologies, and there's a huge number of different methodologies that people will use to come up with forecasts. If we come back onto our graph, then we've got a few others here as well. We've got logarithmic, which tends to kind of go up steeper and then trail off and become flat. We've got polynomial to various orders, which will, depending on how many orders you put into your polynomial, will change what it looks like. They can be quite useful sometimes. We've got power, which again is trailing off, similar to the logarithmic, and we've got moving average, which is generally not that useful. Makes it look pretty faux, so not too bad. We're going to stick with the linear one for now. So this is going to be my preferred forecast. So the only other thing I wanted to show you was how you can combine two things together. So we've got our monthly averages here. We've worked out what our yearly averages should be. So now we're going to combine these two things together. So in our month data, if I scroll down to the bottom, or to the bottom of where our actual data is, you'll see that I've put in the next 4 years of months. So we're going to forecast what the monthly temperature is. So we should be able to see, say, we want to see what the average temperature is going to be next August. We should be able to work that out now because we've got our average monthly temperatures and we've got our average yearly temperatures. What I've done on the average temperatures for the month is I've got the average temperature, and then I've made that a percentage of the average for the year. So over the 100 years, our average was 8.5. And so on average over the last year, January has been 39% of the yearly average. So it would be safe to presume that next year, January will also be 39% of the average. You could, if you wanted to, start doing individual graphs for each month, but I'm not going to in this instance. I'm just going to take the percentages, which I've copied in here. So you'll see January's 40% of the average, and then July's 172% of the average, because it's cold over winter. Beautiful, isn't it? So we're going to put equals, and we're going to take our yearly average that I've already copied in, and we're going to times it by our percentage for the month. And if I drop this down, then that's going to give us a monthly forecast for what the temperatures are going to be, which is very handy. And then if we want to take the last couple of years and this year, we can put it into a graph. So if we take all that, we go to insert, and then in new line graph, you can see then that is our forecast, and it's dropping down over the winter periods, going up through the summer periods, and just popping up and down. You can see the last 2 years vaguely followed this trend, which will be going slowly up and up and up over the years, which is obviously a bit concerning. And I'll leave it up to you if you want to comment on global warming and how you feel about it. See, I feel a little bit like I understand it a bit more now. I've looked at the actual data myself. I found that quite useful. 2.5 meters every 100 years is not a good thing. Future generations, aren't going to be able to have the same kind of beach landscapes as we have and things, which is always very worrying. But I'll leave that for you guys to discuss down in the comments. So thanks for listening, and I hope to catch you in the next tutorial.